our remote learning. This video will focus solely on Chapter 10, Section 0.1. This is intermolecular forces. This is a beefy topic, so we're breaking it up into its own kind of topic to discuss. So up until now, we've primarily talked about intramolecular forces, things that make a molecule, right? Bonds that make a molecule. And we know that we think of the different states that a molecule can exist in. It can exist as a gas, a liquid, or a solid. And that we have a kind of understanding of when we look at a chunk or a sample of a molecule in its gaseous state versus its liquid state versus its solid state, we have an understanding of how those individual molecules kind of interact with each other when it's a gas versus a liquid versus a solid. We know that gases, the molecules in gases, right? If I have a sample of argon gas, the individual argon atoms or molecules aren't having a whole lot of interaction with each other, right? They're all moving around. They bounce into each other, but they bounce off of each other. If I have a sample of H2O liquid, we know that each individual H2O molecule interacts with the other molecules around it. They're not super tightly compacted, but we understand that they're much more closely hanging out together than they are in the gaseous state. And then finally, in a solid state, for example, H2O as a solid, as ice, we understand that there's a different way that the molecules kind of interact with each other and pack and everything like that. So like I said, up until now, we've been talking about intramolecular forces, Ra. And these are the forces within one molecule. So within one molecule of H2O, we have two covalent bonds between the H's and the oxygen. We are going to start talking about molecular bonding. Intermolecular bonding is between multiple molecules. So there is a difference between intra and inter. We're going bigger now, right? Intra is dealing with one individual molecule. Inter is saying here's one molecule and here's another molecule, and how do those molecules interact with each other? So again, intermolecular bonding occurs between molecules. So when we have a change of state, so when we say that like a change of state of matter, going from gas to liquid to solid. So if I have steam, water vapor, and I cool it down into a liquid, and then I cool it down further into a solid, that's still all water, correct? At no point was the steam, the liquid vapor, the water vapor was still H2O. When it was the liquid state, it was still H2O. When it's the solid state, it's still H2O. So the intra-Ra molecular bonds were never affected. However, the inter-Er molecular bonds, or forces, we're going to say forces. They're not real bonds. They're forces. They're attractions. The intermolecular forces are what are going to be affected by these states of matter change. So this occurs with energy. We know that a gaseous form of a molecule has higher energy than the liquid form, which has higher energy than the solid form. And so the more energy we have entering a system as we go from solid to liquid to gas, the more energy there is to break up these inter-Er molecular forces that are holding the molecules together. So the first type of intermolecular force we're going to talk about is a dipole-dipole attraction. Okay, this is an intermediately strength force. So there's three forces we're going to talk about. London dispersion forces, also sometimes called induced dipole. That's the weakest. Then dipole-dipole. And then we have hydrogen bonding. Okay, we're going to start with dipole-dipole because it's kind of the most obvious to us. So dipole-dipole intermolecular forces occur when we have polar molecules. So this type of attraction cannot occur in a nonpolar molecule. It can only occur in polar molecules. So it's an electrostatic, and we know that means we got to think in terms of slightly positive, slightly negative. So if you haven't picked up on this, dipole, the word dipole, we've seen that word before. We know we're going to be dealing with polarities. So just like we've done in our other chapters, you need to know Lewis structure. You need to determine whether a molecule is polar or not to be able to identify the intermolecular forces in it. So what ends up happening in a dipole compound, let's pretend this is a molecule of H2O. Let's pretend this is another molecule of H2O. We know that the oxygens are over here, the hydrogens are down here, right? Slightly negative, slightly positive. Just like if we had magnets, if we put a whole bunch of magnets, like when you were a kid and played with magnets, on a table, we know that all the magnets would arrange themselves in a way where the positives were pointed towards the negatives, negatives were pointed towards the positives. And that's what we're showing here, this attraction. It's not a real bond, it's an attraction. That's why it's got a dotted line instead of a real line. Okay, this is an attraction between this molecule and this molecule. Remember, these are actual molecules, not atoms. We're talking about molecules now. Down here, let's pretend we have a whole bunch of water molecules. The red dotted lines are attractions. The blue dotted lines are repulsions. Think about it. A positive, slightly positive end and another slightly positive end are going to want to push away from each other. So they're in constant flux because of these attractions and repulsions. The next type of intermolecular force that we're going to talk about, I am not a fan of the name of it. I did not get to come up with the name of it. This is the name we've got to live with, but we need to understand what the name means. It's called hydrogen bonding. Now, this is an intermolecular force. It's not really bonding. There's no actual bonding going on between the molecules, okay? So it's kind of a misnomer. It's not real bonding. It's still an attraction. And hydrogen bonding, the intermolecular force that we call hydrogen bonding, is a special kind of dipole-dipole interaction. It's a special kind. It's one where we have hydrogen present, and we'll talk about what we have to look for when we're talking about this. But what we have to think about is we know hydrogen's very, very tiny, and it's also always going to be slightly positive, right, when we have these polar bonds. And if hydrogen is attached to something like an oxygen, a nitrogen, a fluorine, something like this, what ends up happening is we have this super duper dipole-dipole interaction going on. So much so that it's so stronger that we gave it its own name and we call it hydrogen bonding. So we'll look at some examples of this as well. So water is a really good example of this. It's a polar molecule, right? We know water is a polar molecule, so it has dipole-dipole interactions going on, but it also is capable of hydrogen bonding interactions as well. So molecules, their intermolecular forces, they can have multiple intermolecular forces, and many of them do. So when we look at this, we go, okay, I know it's a polar molecule, so it's going to have dipole-dipole interactions. But when I look at it, I go, oh, the hydrogen is bound to an oxygen. This is also going to have hydrogen bonding interactions. And because there's two of them, this means it's going to have the capability of having two hydrogen bonding interactions. And so what ends up happening is it's kind of like a special, more stronger dipole-dipole interaction. The weakest of these intermolecular forces that we're going to talk about are London dispersion forces. These are also called instantaneous dipoles. And these exist only in, they exist in everything, okay? So our water that we have here, our water has London dispersion forces, our water has dipole-dipole interactions, and our water has hydrogen bonding interactions. London dispersion forces are the weakest of those. And for nonpolar compounds, this is the only kind of intermolecular force they have. So let's think about this for a second. Nonpolar compounds that we've run into a lot, think of things like carbon dioxide, methane, butane, propane. When we think about these nonpolar compounds, we start realizing a lot of them are gases. These nonpolar compounds are gases. That means that their molecules, the individual molecules in the sample of that gas, aren't really held tightly to each other, which would make sense because all they have are London dispersion forces, which are the weakest of the intermolecular forces. And these London dispersion forces, also sometimes called instantaneous dipole moments, occur because we have to start thinking about this. Okay, so these are nonpolar compounds, so they're sharing the electrons equally in the bond. However, we know electrons aren't stationary. They're constantly moving. So it's possible for just a second, just an instant, both electrons live on one side of the bond, just for an instant. And in that instantaneous moment, we would have a dipole. We would have a slightly positive, slightly negative. But in the next minute, it moves. And then maybe the instant after that, they're on the other side of the the bond, the covalent bond. And we have a new dipole occur. And this constant moving around is a very short-lived dipole. So it's very, very weak because of that. And it can start to become very, very significant when we have a large number of atoms. So the bigger the molecule, when we're dealing with intermolecular, when we're dealing with London dispersion forces, the stronger the London dispersion force is. It's still the weakest when compared to something like a dipole-dipole or hydrogen bonding, but if I have something like methane, which is CH4, and we know that's nonpolar, and then I have something like decane, which is a compound that has 10 carbons in a row, and the hydrogens all around it, the decane will have a much higher boiling point than the methane because it has more London dispersion forces occurring, because there's those instantaneous dipole moments are happening all over that molecule. So if we have 10 carbons and all the hydrogens around that, that's a lot of opportunities for those instantaneous dipole moments to occur. Where if we only have something tiny like a CH4, there's very few opportunities there. So one of the things that you will have to be able to do come test and quiz time is to be able to relate these intermolecular forces to boiling points of different compounds and explain why we see these physical trends occur at different boiling points and relate it to intermolecular forces. So, again, when we're dealing with London dispersion forces, the big thing you need to talk about here is that we have a non-polar compound. Everything has London dispersion forces. All molecules have it. But the important thing is that non-polar molecules, this is the only type of intermolecular force they experience. So let's think about this for a second. When we go back to our 152 days and we were learning the difference between a chemical and a physical change, we know that a physical change does not change the composition of the material, right? So physical change, the classic one we always think about is ice, like ice cubes of water, melting and becoming liquid water, and then boiling and becoming steam. At no point did the chemical composition of the water change. It's always still H2O. All we did was change, right, the little letter in the parentheses. We went from solid to liquid to gas, but it was always H2O. So those are physical changes. A chemical change is where we actually change the substance, right? So that would be if we went from H2O and we broke it apart and it became H2 and O2 gas, right? That would be a chemical change going on because we changed the composition. So that's something important that we got to keep in mind when we're thinking about these intermolecular compounds or intermolecular forces. So like we said, right, when we go from H2O liquid to H2O gas, this is a physical change occurring. Nothing about the composition of the material changed. It's still H2O. All that happened was it physically changed states of matter. We went from liquid to gas. And this has to do with its intermolecular forces. We know that liquids, when we go back to that first picture we had in this section of our notes, when we have liquids, we are, the molecules are much closer together. And so they have a lot of intermolecular forces interacting. In this case, hydrogen bonding, because it's water, would be the strongest of them. But it also has dipole-dipole, and it also has London dispersion forces. But we know that when we take liquid water and we add heat to the system, that we can make it boil, and then it becomes a gas, it becomes steam. So adding that energy, that heat energy into the system, what we're able to do is disrupt and break apart that intermolecular force, allowing those water molecules to move further away from each other and become a gas. So the breaking up of intermolecular forces relates to a change in physical state. So let's go through and kind of distinguish the difference again between a chemical and a physical change. So an example of a chemical change, right? Combustion would be a good example of this. These are reactants, these are products. The reactants don't look like the products. So we change the composition of the materials. This would be a chemical change. So when we're talking about those dipole interactions, sometimes called the dipole-induced dipole interaction, what we're talking about is, like we talked about earlier, that concept of these magnets, right? The North Pole, South Pole, the positive, negative of the magnets kind of aligning themselves. And obviously, the strength of that dipole will depend on the polarity of the dipole, how strong the polarity of the dipole is. Nonpolar molecules with a greater number of electrons will have increased polarizability, right? So this would be the idea of that London dispersion force where we have bigger compounds. They'll have more of these dipole-like moments. Here is your first door question for chapter 10. So I'm going to give you a moment. Go ahead, pause, try and answer this question. You can try and answer this one. Now, you may be confused with this one, and I want to bring this up. Water has London dispersion forces, water has dipole-dipole interactions, and it has hydrogen bonding. All of these exhibit London dispersion forces. CH4 and N2 and helium only have London dispersion forces, right? They're all nonpolar. So now we're dealing with carbon monoxide and water. Carbon monoxide only has London dispersion and dipole-dipole. Because we know of how the water molecule, what the Lewis structure of it looks like, we know that the hydrogens are bound to the oxygen, which would give it London dispersion forces, dipole-dipole interactions, and hydrogen bonding interactions. Go ahead and take a minute to try and answer this one. Now, like we said earlier, you will have to be able to relate intermolecular forces to things like physical changes like boiling points and melting points and things like that. So this is a good practice to get you going with it, but I will give you the hint right now. There's probably going to be an essay question where you're going to have to relate this. So you want to start practicing now how you want to explain this. This is the end of section 1 of chapter 10. We will be going through chapter 10 in different sections, so look forward to videos 2 and 3 from this chapter. As we move forward, again, please go back and look at these interactions and understand what we mean by the difference between an intra-RA and an intermolecular force. If you have questions, please always come to office hours, email me, and you can get started on your homeworks.